Okay, sir.
ఓకే లైవ్ ఇచ్చారు కదా ఒకసారి వెల్కమ్ చెప్పేస్తాను సారీ
Good morning, dear participants. A very good morning to you all. And I welcome to the third day of this webinar on climate change impacts on water resources and management, environment. And today's first lecture will be given by Professor Rajib Maity. He is a professor in Civil Engineering Department, IIT Madras. So now
IIT Kharagpur.
sorry, IIT Kharagpur, sorry. Then I request our senior professor in our department of Andhra University College of Engineering will introduce you today's speaker to the participants. Sir, please.
Good morning to all. I think you enjoyed the webinar very well. So I think we had beautiful lectures by different people right from Nagesh Kumar garu till yesterday. Pankaj and Umamahesh. Now I welcome Rajib Maity garu. He is known to most of the people for his credentials and nice research work in the area of hydrology and climate related issues connected with water resources. So I'm happy to introduce Rajiv ji to you all. Dr. Rajib Maity is an associate professor in Department of Civil Engineering, IIT Kharagpur. He is known to most of the people who work in the water resources linked with hydroclimatology, because his research area is hydroclimatology, climate impacts on water resources and its management, stochastic hydrology, hydrological applications of satellite remote sensing, and so on. He is a good academician with a lot of track records right from his post-graduation. He is gold medalist in Master of Engineering from IIT Bangalore. He completed his PhD from IIT Bangalore in 2007. He published many books and more than 100 research articles in different journals, conferences, and I'm happy to inform you that he is one among few who got this humble fellowship from Germany. In addition to that, he got Faculty Excellence Award from IIT Kharagpur, Professor Gaude Research Award, Emerging Leaders Fellowship from Australia, Vice Cash Fellowship from India-US Joint Ventures, Institute of Engineers Young Engineers Award, DAD Fellowship, and so on. So we are really happy to see Dr. Maity in this webinar. We should thank him you should thank him for accepting our request to deliver a interesting lecture here. Dr. Maity also serves as Associate Editor of Journal of Earth Sciences, Earth System Sciences, and Journal of Hydraulic Engineering published by Taylor and Francis. So the biography is quite lengthy. It shows his contribution towards academics, So now I invite Dr. Rajib Maity to interact with the participants. So I once again thank the Sri City and Jairam Reddy Garu for their association in organizing this international webinar. Thank you very much. Maity ji, please.
Good morning, everyone. Am I audible?
Yes, absolutely.
Yeah, good morning, everyone. And thank you very much for this introduction. Today, for this next 1 hour or little more than 1 hour, I'll be discussing on a general topic. The general topic is hydroclimatic modeling in a changing climate. However, my specific focus will be on rainfall and droughts. And of course, if time permits, then I can also take you to some other variables. But I assume that the basic part of the climate change impact on water resource in general is already known to the participants, and for the last 2 days in this webinar also, I'm sure there are some parts has been discussed. So my focus through this talk will be to give some new concept and new modeling strategies in this changing climate that is being developed or popularized in the recent past. So first I will take that rainfall component, and then I will go to the droughts part. And of course, in the drought part also there will be 3 different subdivisions against there, depending on different types of droughts. The first one is meteorological drought, then agricultural drought, and then hydrological drought. And of course, I'll share some of the further reading parts where these more details can be found. So coming back, what are the main concept that I told that will be communicated through this talk is the concept called the time varying concept. This time varying concept is basically a modeling strategy that can change over time, because as we know that if something is changing in the environment and we want to model those things, then of course we have to adopt something which also can update it, which also can be recalibrated or relooked into its performance with the changing ambience or changing climate in this concept. So before I take you to those deeper concept, let me gradually give you a little bit of overall research perspective that myself and my group at IIT Kharagpur we undertake different components, and in this, as you know, that climate impact on water resource is one of them. Hydroclimatic teleconnection, this is a concept, and nowadays it has started coming in the news also. We know that what is El Nino, that is happening every year during the summer months. There is some news article comes, what is the status of El Nino. Those are basically have some influence through hydroclimatic teleconnection. I'll come to that. There are other components include GCM and downscaling. GCM stands for either General Circulation Model or Global Climate Model. So there are simulations, there are downscaling. Of course, the bias correction is also included in that. Another component is flood protection and management, then drought characterization and prediction, sea level rise, soil moisture modeling. The soil moisture modeling can also be in 2 components. One is that hydrometeorological modeling or the application of the remote sensing or a blending between these 2. So that also constitute another area, that is the remote sensing applications in this domain. But anyway, today I'll be concentrating on the rainfall and the drought component. The general idea of this entire research component can be very broadly and overall divided into two parts. So if we just start with this slide, the basic concept is shown on the top box that reads that hydrologic variables are significantly linked with the atmospheric circulation. So this is the basic idea of all the modeling that we think of, that we conceptualize, that we attempt to model. So there are this significant link is always perturbed with lots of uncertainty and the hidden complex relationship. So these are very important, that there are some relationship. That relationship is kind of associated with lots of uncertainty, and that relationship is complex, and the relationship is sometimes hidden, so that we need some mathematical approach to take that out. So this hydroclimatology area, its basic focus is that if there is a change in the atmospheric circulation, atmospheric pattern, then if we can have identified some modeling strategy, then when the input changes, can we see some changes in the output? And if we assess that change in the output with respect to the current scenario, then we can find out some impact of the change in the climatic scenario. Now there are two parts, as you can see in this slide. One is in the green arrow and other one is shown by a blue arrow. And in the blue arrow, there is another box in between that reads that simulation through general circulation models. So what we do, this concept is through some physically based concept, we try to model it, and we run the entire globe-wide network or the gridded models, and those are popularly known as general circulation models. And we take out their simulation output and find out how they are changing. And of course, there are some challenges. I'll come in a minute. On the other hand, in the green part, for a smaller scale, particularly when we talk about the hydrological applications, we need the information at a very, very small scale. This very small scale again is subjective. When I mean that very small scale, I am talking in terms of the continent or the entire world. So we know that our water state may be very small when we plot it even on a countrywide map. So in such a small spatiotemporal scale, sometimes we use some statistical relationship between those atmospheric pattern and the hydrologic responses. And if we are confident in this relationship, then we are ready that if there is a change in the input, what is the change in the output? So these are the major things, and both the paths have their own merits and demerits. The first thing,
Professor Maity.
Yeah.
Sir, your slides are not changing. It is still the first slide is there. Yeah, now it is changing. Right.
Then there may be some problem in the full screen mode. Should I move in this way? Is it the first slide now? Dr. Reddy, can you confirm that is the first slide?
Yeah, this is the first slide.
And is it changed to the second one?
This is second one, outline.
Okay, fine. So let me very briefly
on my research area. Yes.
Okay.
Yeah, please continue with this current mode. It will be okay.
Is it legible, right, at that end?
Yes, sir. Yes, sir.
Okay, fine. And let me proceed with this one. I don't know why the full screen is not working, even if I am here on the full screen mode. Okay, so in the last 5 minutes, I gave you the overall outline. The two things I'll cover, one is the rainfall, other one is the drought, and I took you to in an overall nutshell of this. My research area has the different components. That is the climate impact, hydroclimatic teleconnection, GCM and downscaling, along with the bias correction, flood protection, drought characterization, sea level rise, soil moisture modeling, and remote sensing applications, where my students and my group here is working on. But today I'll cover the rainfall and drought component. The overall, this area have two parts. As I was telling, there are two parts. One you can see as a blue arrow, other one is in the green arrow, and both the paths have their own merits and demerits. Just I want to cross check once. Am I on the slide number 5 now? Am I on slide number 5 now, Dr. Reddy? Hello? Am I audible there? Hello? 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 Hello?
Audible. Hello?
Hello? Am I audible there?
Yes, sir. Yes, sir. Your PPT now went off.
So I don't know, means somehow I understood. I'm just saying that whether slide number 5 or not.
Yeah, slide number 5 was visible that time. Now it is went off. Yeah, now it is visible. Slide number 5.
Is it visible now again?
Yes. Yeah, it is visible now.
So maybe just I'll just stop in between and just cross check whether it is working or not.
Yes, sir. Yes, sir.
Yeah. So this is what I was talking about the last time when the slide there was some. Sorry for this interruption. I don't know what is happening. It is not going even in the full screen mode. But I hope that font size is sufficiently large so that it is legible at that end, right?
Yes, sir.
Yeah. So the two paths that I was discussing, one is through this GCM simulation, other one is through some statistical modeling, and both the paths have their own merits and demerits. And if I go to the next slide, slide 6, please confirm it is changed there, slide 6. Is it slide 6 there?
Slide 6 is now visible.
Oh, is there a delay now? So when I'm saying that is slide 6, so there is a delay significantly.
Yes.
Okay, fine. Let me go then slowly. So here I am discussing what are the shortcomings from this so far the general circulation models are concerned. So its potential is good so far as the continental or the hemispherical scale to the local subgrid scale. Local subgrid scale, what I mean that the grid size for a GCM may range from 200 kilometer to 300 kilometer. But sometimes we need the information much finer scale, say 10, 20 kilometers or even 50 kilometers. So there it is weak. Secondly, the free tropospheric variable to surface variable. That means when you go to some higher altitude, there those variables are better simulated by GCMs. But when you come to the near surface thing, those things are not that well. Similarly, for the meteorological variables like wind, humidity, pressure, temperature, these are relatively better as compared to the hydrologic variables like precipitation, runoff, and soil moisture. But if you see all the three cases in the later part, that is my local subgrid scale, surface variables, and the hydrological variables are more important so far as the water resource applications are concerned. So we have to go for some downscaling and bias correction. These are the shortcomings of the other side. And another one is that when you go for some smaller scale, sometimes the feedback from the large scale may be missing in that type of model. So as I told, both the side have their own merits and demerits. Now, a little bit discussion on this hydroclimatic teleconnection and hydrometeorological association. As I was mentioning that nowadays in the news also, it has come that El Nino has a significant impact on Indian summer monsoon. So this hydroclimatic teleconnection, it means the significant association between the hydrologic events and the large-scale atmospheric circulation pattern. So one such large-scale atmospheric circulation pattern is El Nino Southern Oscillation. and which are widely separated in a planetary scale. So this El Nino is an event in the tropical Pacific Ocean, and it has some impact on the Indian summer monsoon, so which are means thousands of kilometers away from each other. That's why this term is called hydroclimatic teleconnection. Apart from
సెమినార్లో
that,
ఉన్నాను. మీ వాడు
there are
వింటానంటే విను, ఇవి అన్ని సివిల్ వినమను వెబినార్ ఆన్లైన్లో లింక్
so
పంపిస్తాను.
there are some hydrometeorological
ఐఐటి
postings are
ఖరగ్పూర్ నుంచి సివిల్ డిపార్ట్మెంట్ ప్రొఫెసర్ ఆయన చెప్తున్నాడు. గత 2 రోజుల నుంచి జరుగుతుంది. మరి మీ వాడు వింటానంటే ఈ సండే వరకు ఉంటుంది.
Hello.
Sorry, am I audible there? Actually, there are some
Yes,
sound
yes,
from-
sir. You are audible, sir.
Yeah, okay.
Yeah, you are audible.
Apart from that hydroclimatic teleconnection, there are some local factors are also comes into play, that is called hydrometeorological association.
లైవ్ లో ఉంది, నేను మళ్ళీ లింక్ పెడతాను చూడండి.
Hydrological and the local meteorological variables, and this is called the hydrometeorological association. So these two things are coupled and raise to lots of uncertainty in different analysis, and our focus is one of our major focus in this, or major challenges in this field is the associated uncertainty. So if I just summarize that overall issues and challenges, the first one is the dynamic nature of this cause-effect relationship. That is, even if I develop some model, that model may change over time due to the change in different conditions, not only in the climate as well as the water state conditions may change over time. So that is what we call as the dynamic nature of the relationship. So that is sometimes very challenging to capture using the traditional modeling approaches. Uncertainty, we have discussed that since there are lots of influences may come, which are sometimes it is known and sometimes it is unknown, so that amount of uncertainty associated is very high, so the proper quantification of uncertainty is necessary. Third one is the consideration of the non-stationarity. The non-stationarity here, what we mean is that the statistical properties of any particular variable may change over time. So as we know, that the most known example to the audience may be the global warming. As we know, the global mean temperature is gradually changing, so that means that time series the mean is changing over time. Similarly, any other statistical properties, the mean, standard deviation, or other things, if it changes over time, we call it non-stationary. Now, while modeling the non-stationary time series becomes very challenging. Next point is to the large scale to the basin scale. Even if we have some potential, some reliability as a large scale simulation, but we need, so far as the hydrology and the water resource is concerned, we need to map it from the large scale to the local scale. That is also another major challenge. And finally, if we can identify some potential input, whether we can improve the prediction performance or not. I am not saying that these are the only issues or challenges listed here. These are some of the important issues or challenges that we have to take care, whatever the modeling attempts or modeling approaches in this domain that we undertake. As I started with, we'll take two different parts today for discussion. One is rainfall and other one is drought. In the rainfall, the new concept that I am going to introduce to the participants is called the time varying concept of hydroclimatic analysis. Here, the time varying, what I mean is that traditional modeling approach, once I develop the model, that remains same for throughout the testing period. Now here, is it possible to modify the model itself and look into it? Now there are some development is already there so far as the model parameters are concerned. We update the model parameter in a basin paradigm, but a proper time varying model should also look into the importance of the input first, whether some input over the time has become less relevant or not, or some other input has become more important or not, so that input as well as model parameter both may change over the time. So why this is important? The important are there. I'm not reading the slides, but some of the key points I want to convey to the participants is that the spatio-temporal variability of this rainfall is huge. As you know, even if I take a single country like India, you know that how much variation is there from the east to west and north to south, and at a particular location also over the time it may also change significantly. So this jointly it is known as the spatio-temporal variability. and we have seen different cases of below normal and above normal monsoon in India. So the considerable effort we just put is called the long lead monsoon prediction. The long lead means if we can just see what is the status in the upcoming seasons and all, then that will give a lots of information even for the government or the policymakers to get prepared in that direction. However, as I can telling that when the relationship becomes temporarily varying, it becomes challenging. So still, if you just find out every summer we get some forecast of this ISMR, but in the recent past we have seen that there are lots of whatever is being predicted, there is a failure in this case. So that is what we hypothesize, that there is a temporal variation in this dependence, and we coin a term called the conditional dependence, and there is another term also called the conditional independence. I'll discuss those things. So if we can identify the temporal evolution of this association and change, that may help us in the better modeling strategy. I'll give you one example in this application. Let us first of all understand two large scale indices. One is the El Nino Southern Oscillation and other one is Equatorial Indian Ocean Oscillation. These two concepts will take through the hydroclimatic teleconnection mode, and we want to import the time varying concept in these two. At this stage, I want to just mention to the participant the El Nino and this Indian Ocean dipole are not the only two large-scale atmospheric patterns across the globe. There are many other. You can see in this slide there are North Atlantic oscillations, specific decadal oscillations, Southern annular mode, Atlantic multi-decadal oscillation. Like this, there are many others. But so far as the Indian monsoon is concerned, most heavily researched two large-scale indices are, one is El Nino, and all are coupled. Coupled means there is one oceanic component, another atmospheric component is there. So like that, El Nino is the oceanic component. It is coupled with the atmospheric component, which is known as Southern Oscillation, and jointly it is known as ENSO, that is El Nino Southern Oscillation. Similarly, the atmospheric component of Indian Ocean dipole mode is known as EQINO, Equatorial Indian Ocean Oscillation. Let us give a little bit of background for this one. I don't know, there is one animation, but since I cannot go to the full screen mode, this animation will not be shown. But I can take you to the next slide where you can see the SST pattern in the normal year and with respect to the El Nino year and the La Nina. La Nina is the opposite of this El Nino. And it is basically, if you see the second row, it is the anomalous warming of the sea surface temperature is known as the El Nino condition, and anomalous cooling is known as the La Nina condition. And it is coupled with this atmospheric pressure field also, which is in the last row. And once it is on the western part of tropical Pacific Ocean, and eastern part of the tropical Pacific Ocean is showing the higher pressure, which is the atmospheric pressure field and reflected through southern oscillation. It has an impact of sea level height change as well as the atmospheric circulation. This is most important, that's atmospheric circulation part. In the middle, you see that is a normal Walker circulation. Now during the El Nino condition, the rising limb of this Walker circulation shifted towards the east, and in the La Nina condition, it further shifted towards the west. And this circulation is huge in the sense, in the planetary scale, almost 1/3 of the entire equator of the globe, this circulation hampers. So it has a global impact on different parts of this country. Here you can see in terms of these rainfall deficiencies, low river discharge, surplus rainfall at different parts of this world and different seasons. So if you concentrate on the India in the June to August, you will see a dry condition is shown here. So that is the impact of El Nino, and that's why in the news, if there is an El Nino year, India is expected to receive something lower than normal rainfall. Similarly, the opposite we see in the case of La Nina, when we see is the higher than normal rainfall. So how these indices are being measured? There are different zones are identified in the tropical Pacific Ocean, and average of the sea surface temperature anomaly is used as an index. And for India, we mostly use the Nino 3.4. This Nino 3.4 zone is shown in this slide in a black rectangle, dotted rectangle, and it is basically overlap between two zones called Nino 3 and Nino 4. That's why the name comes as Nino 3.4. and the 3 months running mean of this index is known as oceanic Nino index. Both are being utilized as an index of El Enso, so far as Indian thing is concerned. Now, if we come to the Indian Ocean side, we see another such coupled mode, which is known as Indian Ocean dipole. And if you can see, once on the eastern side and others, and in some other area on the western side, the sea surface temperature increases and the convective activity also increases. Wind pattern in the equatorial Indian Ocean is also changes. Either it comes from the east to west or west to east, depending on whether it is, one is called the positive dipole mode and other one is called the negative dipole mode. So it has an atmospheric component which is known as equatorial Indian Ocean oscillation. You can see in the red zone, the red rectangle over which the zonal wind is considered its anomaly, and negative of the anomaly is considered equiwind, which is the index for this equatorial Indian Ocean oscillation. So far I have discussed two large scale indices. One is ENSO, another one is Equino. Now, thing is that how to extract this information from these large scale indices and apply it in some model to predict or to model this Indian summer monsoon rainfall has a long history, long research and all. What I am going to present, what new thing I am going to present is called the time invariant versus time variant approach. One is that the most of the traditional modeling approach, I repeat once again, that it develops and it remains same. Now, thing is that since there is a changing condition in the environment or in the climate, it is the modeling strategy can also be time variant. So there are two things has to be considered. One is that whether the inputs should also get changed as well as the model parameters should also get changed. So that's why the focus here is that what about a time varying model for ISMR using the uncertainty quantification, of course, that is also important. And I'm not going into the details of this study area, is basically the entire India, no doubt, and its data used. We have used the data from 1950 to 2009, and the concept of this time varying approach, let me go. One is that it is called the time varying association of the predictors, means we have identified the predictors with different lags and whether there is any change in that predictor set or not. Secondly, the conditional independence. Now, this conditional independence I'll just discuss in a graphical mode, so that will be more useful. And then in the modeling, parameters also will be changing. And the third concept that we'll see, that is called the optimum recalibration interval. So what should be the optimum recalibration interval? That is, I need to relook into the modeling strategy and I need to update that. Let us come to this graphical flowchart kind of thing so that I can explain this concept. So I want to draw your attention from the first this graphical interface, where you can see that there are 4 nodes are shown here. Suppose that there are 3 inputs and 1 is target. In the traditional modeling approach, all these variables are connected to each other, and this is called the saturated model. Even if I take a simple multiple linear regression model, and we know that we have different inputs and 1 target output is there, but it is possible to show that some of these edges, means some of the association are not significant statistically. So it is called the whichever is connected directly with the target is called the parent variable. Here I can show in the blue circles, and other things which is shown is in a green one, it is called the conditionally independent variable. So this conditionally independent variable means that if I have this blue circle, I don't need this information. So this information comes via this information. For example, if I have the runoff information, I may not need the rainfall information in a rainfall runoff modeling. So that means if someone can give me reliable runoff estimate, then rainfall becomes a conditionally independent variable. But in case when the runoff information is not available to us, then for stream flow, rainfall becomes important. So here, of course, we are considering different large-scale inputs, and the ISMR is the target. Now, this is one of the things to find out the prune this predictor set. But the time varying concept is that even this variable may change over time. So that means if I develop a model over a climatological time scale for 30 years, then I have to identify how long this model can run without any disturbance. And it depends on the which problem you are handling with. So far as the ISM or Indian summer monsoon rainfall is concerned, it will have one optimum prediction recalibration period. If I change the model to a basin scale rainfall runoff model, that prediction time horizon may change. But thing is that to identify the optimum value, that we have to run it for the different years and find out which one is the best. I'll come to that point again. But little bit of this mathematical background, as I was telling, this is the saturated model, and there are some age exclusion deviances through this correlation analysis and the partial correlation analysis, from which I can identify some age strength, and finally, depending on the age strength, the sum of the ages can be dropped out, and the parent variables and the conditionally independent variables can be identified. I'll show you the example with respect to the Indian summer monsoon rainfall. Similarly, for the model parameters also that can change, and here for this specific problem we have utilized a sieve-Hein copula, but I'm not saying that you have to use only the sieve-Hein copula, there are other models also, but the concept of changing the input set is important here. And the second important thing is that optimum recalibration interval that I was telling. So how long the model can work nicely before you need to recalibrate it, that is the next concern. Here, so far as the Indian summer monsoon rainfall is concerned, you can see that in the x-axis, I don't know, it may not be legible at that end, but we have run this model for different cases, the 1 year, 2 year, 3 years like this, and we have find out the Indian summer monsoon system is so dynamic that you can go maximum up to 3 years before you can say that a model you need to recalibrate. And we can see that a pure peak so far as the 3 years is concerned. Here on the right hand side, this is called the heat map, how your model is performing, and depending on this criteria, there is a clear indication that after every 3 years you need to relook into its input as well as its model parameters. And that is what is called the 3 years may be selected as the optimum recalibration interval for this. So how does it impact on this one? Before I go to that, I want to show you how the graphs looks like for a particular month. And these are the different inputs. The entire set is the different input that we have considered. And we can see that for the target, there are only 2 direct association is there, and all others are connected via these 2 variables. And the EN stands for the ENSO and EQ stands for the Equino. And the lower small numbers are basically the lag in months. So this is one of the example. And this table is showing that how with respect to the model development period, if I change this model development period, how these models are also the input and the model parameters are changing over time. And with the model, you can you can use that model for some period. Again, you need for this recalibration. This diagram is showing how this model parameters, a particular parameter is changing over time. You see that these are called the age strength. Age strength means in a graphical modeling paradigm, how the age or the association, the strength of the association is changing, and you can clearly see that there is a gradual drop of this association or some other variables may pop up. Similarly, the left hand side is showing for this El Nino and right hand side is showing for this Indian Ocean dipole mode, which is the atmospheric component is Equino. This is a 3-dimensional plot. Even in the 2-dimensional, you can see how is it becoming relevant and again becoming insignificant. This red line is the threshold, statistical threshold, over which you can say that it is significant or not. One is for ENSO, another one is for this Equino. So if I just take you to what is the final end product of this one, and this is what is showing that different comparison. If I take the time variability or if we don't take the time variability, how much is improved in this modeling strategy. Similarly, just to show you that that 64% in terms of this RMSE in the anomaly is being improved if we shift from the time invariant approaches to time varying approaches. And on the right hand side, if we see this cloud, and this cloud is basically the uncertainty range of this prediction variable. So it is not only giving a specific value, but also it gives a range also. This slide is compared with the different traditional approaches with respect to their time invariant concept as well as time varying concept. We have taken one AI based model that is called the support vector regression. Other one is the sieve-Hein. Sieve-Hein also have 2 parts. One is I can use it as a time varying concept or the time invariant concept. and we have shown that the time invariant, with respect to the time invariant concept, how the time varying concept is improving this performance. This is just one of this example, but this concept is very recently, in this last week itself, we have conveyed to this water resource area, specifically in the stream flow prediction, and we have shown that how this time varying concept is improving their prediction performance also. So as I was discussing, the major findings for this case is that the temporal networks, that is the this time varying association is captured through these temporal networks and through that optimum recalibration interval. These two things, if we take, and with respect to the ISMR problem, that is Indian summer monsoon rainfall, 64% more accurate performance in terms of this RMSE is shown to be achievable. So instead of this large scale, we can apply this concept to our local scale, our local variable, our local small scale analysis as well. And this is not only for this sophisticated or high-end statistical model, we can apply it to as simple as for any AI, as well as from the even as simple as the regression based models also. Maybe I'm running out of time. I'm quickly going to these droughts, and after I finish this one, I can take some of the questions if you have in this part. So drought characterization and the hydroclimatic analysis is the new concept that I am going to portray in this one. And we know that what is the definition of this drought, and it is called the creeping devil. Creeping devil means we don't even know that when it is properly being onset, so that we take. So the flood can be seen, but the drought can be realized. That's what people say. And it is only the agony of the farmer in the middle of this drought-stricken farms, where it basically shows some social point of view. And there are lots of news in the middle of the year we heard from different parts of our country. So a proper modeling of this droughts is concerned. So our contribution towards this drought analysis in the three different groups that I was starting with is the meteorological drought, agricultural drought, and hydrological drought. Meteorological drought deals with rainfall, agricultural drought with soil moisture, and hydrological drought deals with the stream flow, groundwater storage, reservoir storage, and all. Coming to the meteorological drought, what is our specific contribution in its characterization with respect to the Indian hydroclimatology? We all know almost that the standardized precipitation index is one of the popular index that we utilize for its characterization. And if we take one sub basin or one homogeneous monsoon region, any part from India and one part from US, and we do some periodicity analysis, and it is obvious to come out there is a strong seasonality so far as the Indian monsoon is concerned. And there is a 12-month peak we see, and it is obvious we don't have to do any analysis to show that in India we have a strong seasonality in this rainfall pattern. But if we go to some of these provinces in US, there is no significant periodicity, and here lies the motivation of this one. The SPI, the standardized precipitation index that was developed, might be in some rainfall studies in Arkansas, US, where there is no periodicity. And in fact, in India, there is a strong seasonality in the rainfall pattern. So can we blindly utilize SPI in the Indian context? And if we use, what is the consequences in the interpretation? So that is the motivation from this drought characterization in this giving the local climatology into the concern. So what is our main objection or motivation behind this development is the local climatology has to be incorporated in the drought characterization so that the proper value comes out. So this is, we have developed a new concept that is called the SPAI. There is a standardized precipitation anomaly based index with respect to the SPI. I am not going to use mathematical formulation on all. I can share those documents and that can be referred to. But I just want to show you that what is the improvement in terms of this SPI and SPAI. If I just take two examples, one is on the drought side, the other one is the flood side, then I want to draw your attention for this January 1964. If we calculate the SPI, the value will become minus 2.17. And let me tell you, the SPI ranges from +3 to -3, and -2 is a severe drought. But the no no drought related consequence was recorded in that month. And I just want to draw your attention to the month January. And in India, in January, even if we don't receive much rain, we don't care. So this minus 2.17, which shows a severe drought in January, may not have that much social implications in India, because here climatology is different. But so far as the August is concerned, which is a peak monsoon month, if there is a small perturbation in this rainfall, then there will be a huge perturbation in our agricultural productivity. And SPI is calculated minus 2.4, which is a severe drought. Now, if I calculate the SPAI for January 1964, it becomes minus 6.4, and for this August 2009, it is minus 2.54. What I want to focus here is that the SPAI, where the local climatology is considered, it can show you the proper drought related indices, in the sense that August is really a drought, and whereas the January need not be, even if there is the SPI is showing something differently. Similarly, for the other side, means the wet side is a flood. In the January 1967, it was 2.1, is a huge flood is supposed to be. Similarly, September 1978, maybe our parents or grandparents knows that the 1970 was a huge flood was there in India, and there was a lots of life loss, and this agricultural loss was then there. And this 2.12 and 2.10 both are, so far as the flood is concerned, are more or less same index. But so far as the SPAI I calculate, where in the January 1967 it is 1 and September 1970 is 2.4. So it is always recommended that so far as the local climatology, in this particularly in this climate related studies, the local climatology has to be incorporated to properly characterize the SPAI. We have also shown that this SPAI is basically the more general term as compared to SPIs. That means whatever is supposed to be revealed in SPI will also revealed in SPAI, but the local climatology will not be revealed in SPI, whereas in SPAI it will be revealed. So we have taken three components. One is the Gangetic West Bengal, Arakasa USA, and a random variable. So you see, if it is a completely random, means there is no periodicity at all, both SPI and SPI are same. But if there is a periodicity, then it shows different indices and different ranges for these 12 different months, so which is very important for a proper characterization. So in Indian hydroclimatology, the standardized precipitation anomaly index is recommended. Coming to the next, to this agricultural drought, which is related to the soil moisture. Here what we have done, we have developed a new index which is called the drought management index, and the drought management index relies on the three different statistical components. One is called reliability, resilience, and vulnerability. So reliability means the soil moisture, if it goes down, how long it stays in the satisfactory stage and the not satisfactory stage, and we have to take a datum, and we have taken the datum as permanent wilting point. And if it is above the PWP, it is a satisfactory stage, and below it is unsatisfactory stage. So there are three things. One is the reliability, second is the resilience. So even if it goes to the drought, how quickly it comes back. And vulnerability means once it goes to the drought, how severe that drought could be. So if I just take this one, we have developed one index. I'm not going again in the mathematical details now. So this index is called the drought management index. This drought management index is a long-term quantification now. What happens, so whenever we just put some drought characterization, it gives what is happening and what has happened. Here the focus is what is going to happen in next 5 years, so that I can take some policy changes for that location. This is where the role of the DMI will be played. We have tested this model at different locations of India, even from the Rajasthan, which is the drought proneness is high, and as well as is the northeast, where the heavy rainfall, and we have shown that it is the drought proneness of a particular region is properly characterized through this drought management index. Now, if I take the 5 years period, how it is changing over the time, how the trend is over the time, then you can see that from the 1965 we have done one analysis, and this drought proneness, so far as the history is concerned, the southern peninsular tip, or this in general, the southern part is showing more drought proneness as compared to the northern part. However, we have done this analysis with the GCM simulation for future also, for the different continent, and there we have shown that there are some parts of this continent is showing a decreasing trend, increasing trend, and so far as the India is concerned, it is showing a more or less stable range. But we have to remember that the India, this stable range, this last one, is basically a combination of the North India and South India. The moment we separate these two and find out the local analysis, then the differences is being visible. How is it changing in the northern part of India and the southern part of India? I'm going to the third part of this hydrological drought, which is related to the stream flow. And here in this hydrological drought, our contribution is that what are a new term called the drought triggers. Drought triggers means it is the prevailing meteorological condition in this month, so that I can foresee what is going to happen in a basin for the next month. So if I can tell that if the atmospheric conditions are like this in this month, be ready that next month is going to happen like this. So this is what is called the drought triggers, and we want to find out these drought triggers through some analysis, and I will just show you some of the results. Here there are some mathematical, the two basins has been taken from US, and these are the most important part. These are the fairly small basins, that is, it is a very smaller spatiotemporal scale this model can be applied to. And again, I'm not going to the much details in this one, but only thing in the drought characterization, there are different categories of this drought: D0, D1, D2. So number increases means it becomes a moderate to severe drought. And so far as the characterization is concerned, first of all, whether these drought triggers are properly identified or not, that we have seen so far as the different drought values are concerned or drought categories are concerned. Again, I'm skipping those mathematical part, and rather I want to just show you that what is the final product that we got from this one. Yes, these are the things. We have taken, say, 7 hydrometeorological variables, and we want to conclude. So, and these variables are, say, soil moisture, precipitation, runoff, evaporation, temperature, sea level pressure, and wind speed. Now you see the first 3 are the soil moisture. Maybe it is not legible at that end, but let me read it out. This is the first one is for soil moisture, second one is for precipitation, and third one is for runoff. And for these 3 things, you can see there is a wide band that I can see. Whereas for the last one, there's evaporation, temperature, pressure, and wind speed. This band is very narrow, and there are different colors are there. These colors are basically different drought strategy. So how to interpret this graph is that the x-axis is different 12 different months, and y-axis is the status of this variable. So in a particular month, if the soil moisture is in this range, if the precipitation is in this range, runoff is in this range, then that particular color, that particular drought category is expected in the next month. And the second conclusion is that if this band is wide, then I can have some meaningful conclusion. Whereas if the band is very narrow, that means it is not giving any more meaningful result. In the sense, it's almost the same value is indicating all different types of drought. That means for this specific basin, soil moisture, precipitation, and runoff are the 3 important precursors that is more meaningful to conclude what is going to happen in the next month. But here there is a caution that this is maybe applicable for this specific basin. Now this analysis has to be carried out for the other basin to find out which variables are becoming more important. Number 1. And number 2 is that we have the data for all 7 variables in this basin, but there could be some basin where all these 7 variables may not be available. If the runoff is not available, then maybe the evaporation becomes more important, as I was started with this discussion. So this is for the one watershed, and this is for the second watershed. So coming to this concluding remarks, though this time varying concept in this domain has been identified. So, and this is not only for the large scale, at the basin scales also this concept can be applied now, and for a proper modeling in a changing climate. Second thing, in the drought characterization, there are 3 things I have discussed today. One is the meteorological drought. In that one, it is recommended to incorporate the local climatology in the drought characterization so that interpretation becomes easier. So SPAI is one of the indices where the local climatology is incorporated. So the interpretation becomes easier, and the differentiation between a low rainfall month like January or February with respect to the high rainfall month, that is a July or September, can be differentiated through this index. Second one is the DMI, the Drought Management Index. It is not only that characterization, we need to take some policy decision for the next 5 years or so. So in that case, so far as agricultural drought is concerned, this Drought Management Index can be utilized, and the climate simulations, the simulation outputs can be utilized to find out, to identify, to characterize the drought proneness of a region and how is it has changed in the last 5 years. So this drought management index can be utilized to identify the drought proneness of a region and how it has changed in the last 5 years.
At 11:30.
Okay. No, it will be done. I think before that, definitely it will come.
Sir, sir.
But the moment it comes, then I will contact you again.
Yeah, please, sir.
Sure, sure.
Dear participants, please stay on to the YouTube channel. There is some network problem at speaker's side at IIT Kharagpur. When the network restores back, and we will here Professor Maity will be again continuing with this lecture, and he will also answer some of the questions you have. Please stay tuned to this link, and whenever the network restores, he will come back again to the live. Sorry for the inconvenience, and please excuse us in this one. It's a network problem from the SAR side. Thank you.
ఇంకా అంతేనా సార్? మళ్ళీ అది వెబినార్ అంటే ఫస్ట్ మనం గూగుల్ వాళ్ళతో మాట్లాడుకోవాలా?
కాదు, వీళ్ళు యూట్యూబ్ వాళ్ళతో మాట్లాడారు.
మెయిల్ పంపిస్తే వాళ్ళు
హలో, హలో. కరెక్ట్, సౌండ్ వచ్చింది కదా.
Hello, Rajib sir. Hello, Professor Rajib. Can you hear me? Hello. Hello. Professor Rajib, can you hear me?
Yes.
Yeah, Professor Rajib, can you hear me?
Yeah, I can hear you, but am I audible there?
Yeah, you are audible.
So actually, I am on my একই হবে। Hello, audible?
Yeah, yes, sir.
Yeah, actually, I'm trying to change from
Yes, yes.
one network to another network if it works. Actually, I'm just on the last slide and maybe on the last concluding remarks. If I'm audible, then I'll continue. Should I?
Yeah, please go ahead, sir. You are audible. Please continue.
Yeah. So the last two
Yeah,
things
please
I'm
continue.
extremely doesn't happen in the once in a while. For some time it happens. But anyway, so drawing in this, I just told it is for the long-term planning. Long-term here means the 5 years, and finally that is applicable for the very, and it is useful also. Climate pattern or the meteorological in this month, just to see foresee the one in the so that is the concept of the drought trigger. So these three things, there are few this slide, and you can see this towards there, and with this and for the any you can আসলে এটা মনে হয় টেক্সট মানে বড় সড়ো ব্যান্ডউইথ পায় মনে হয় এটা। Yeah, actually I have done. I don't know whether how far it was broadcasted.
Sir, if it is done, there may be some clarifications or questions from the participant side. I request you please have that questions.
Yeah, means definitely I'm here. So if I can hear, then I will definitely answer.
Yeah, they will send you on the screen the text messages.
Yes, that will be better. Yes, that will be better. If they can send some email and all, or some, you can just
Not
share my
like-
contact details to them.
It will be appearing on your screen. Somebody sends you the questions.
ఇన్ఫర్మేషన్
Support করবে। Dr. Reddy,
Yes,
can
yes,
we have
sir.
this session after some time? Power is not yet come, and I am not sure how long will it support from my UPS. It may be
Okay, sir.
switched
Okay,
off.
sir. Okay,
So,
okay, sir.
Will it be
Anyhow,
possible
you have given
that
the
they can?
email ID. If somebody is there, they can send you the questions by email.
Sure. They can send by email, no doubt. And
Yeah.
if the power comes, I'll contact you over the phone to you, and then I can connect it again from here. Otherwise,
Surely,
the
sir.
UPS is giving the sound. waste of any.
Yeah, please, sir. Okay, sir.
Okay, then. So
Thank you.
with this,
Thank
I'm
you,
just temporarily.
Participants, sorry for the inconvenience. There is some small network problem from the speaker side. And the next section, I think we will close this section of Professor Maity, Rajib Maity. And next section, next talk will be at will be at 11:30 by Dr. S. Chidambaram. He is from Kuwait Institute of Science and Research, Kuwait. He will be joining at exactly at 11:30. Please stay tuned to our channel, and we will come back again at 11:30. Thank you very much. And I think there may be a feedback link is also given. Try to do the feedback also. And thank you very much.